Okay, so in the last video, we discussed about the basis of assembly language and the basis of shell coding, which is very essential for writing exploits if you want to learn exploit development. Now, the focus of this session, this video is again the Linux platform, which is, we are talking about the 32-bit here. So let's see what we are left with. So we covered assembly language and shell coding. Now let's head to memory corruption vulnerabilities and let us see how memory corruption can be leveraged for arbitrary code execution. So here we are. So memory corruption vulnerability is a vulnerability where you are able to corrupt the memory of the target process, which means by some method, which is generally the input and which we are looking at in this case, you send an input which is able to overwrite adjacent places and corrupts some of the memory which was to be used by the process, such as a stored return pointer on the stack, which is when you call a function, the address of the next instruction after that call to that function is stored on the stack, and if you overwrite the stack too long or too much, then that value may be overwritten, which will result in when you are returning from the function which was called, and since you overrode the return address, it gets corrupted. So that is in essence kind of our focus, memory corruption. So we try to control the execution of the process so as to execute a shell code or our injected payload, which we call. Then memory corruption is actually a class of vulnerabilities, and it has various subclasses such as buffer overflows, uninitialized buffers, metadata corruption, and integer overflows. Now, what our objective in this series is buffer overflows, but let's talk about the other things for a moment. Now, uninitialized buffers are the buffers which you have in your function, which have not been initialized but are used. For example, you declare a variable integer x, and then you just use x to compare something or to take input or something like that, or even multiply, whatever you want to do. And since you have not uninitialized that, in most of the cases, since the buffer is on the stack, or since the local variable is on the stack, it contains some previous values which are generally said to be garbage values because they are not of our current use, but which may be residue of the previous stack frames or whatever. Now, if somehow you are able to control that, then you can get arbitrary code execution depending on other things in the environment. Then you have metadata corruption. Now, metadata corruption are most commonly seen in heap overflows, where you have allocated some memory using malloc or things like that. Now, what malloc does is it allocates a chunk of memory, but along with that, it adds some metadata so that it can be managed by free and other things, memory management things. So when you are overwriting the buffers in the heap, you can also write past the buffer as you can do in the stack based buffer overflow, but if you are overwriting the buffer which was allocated next to the previous buffer, what you have to do is you will pass through, or your data will pass through the metadata before it overwrites the actual buffer. And if the metadata is corrupted, then the execution of the process aborts. So in essence, you have to very carefully control the metadata if you want to exploit these class of vulnerabilities. We will look at heap overflows in upcoming sections, probably after 4 or 5 videos, I don't know, but yeah, we'll sure be looking at heap overflows and other kind of stuff. Now, integer overflows are again, since integers have a property which is resetting. So once you have reached the integer max limit, or a number max limit, for example, an integer is 32 bits on a 32-bit machine, and if you assign a value 2 raised to the power 32 minus 1 and you add 1, then it will get to 0, kind of that thing. So yes, now integer overflows are kind of a different thing. You can in effect control the integer overflow and then control the size of buffer or size of the override, but in essence, since it starts with integer overflow, we call it plain integer overflows instead of just calling it the buffer overflows. Now moving on to the buffer overflows, this is our focus of the current session. In the next session, we will be looking at how what can happen if or what to do if we have a very limited space, or if we don't have enough space for the shell code. And the second scenario we will see is what to do if we have a non-executable stack. You have space, but you cannot execute your shell code because the stack is non-executable. So we will look at that now. Time to talk about the buffer overflow. If you have not ever done the buffer overflow, now let's explain this. A buffer overflow is a space in memory, usually a variable or a buffer, a character array, things like that. If it obtains more data than its capacity, for example, you have a character array which is of 12 bytes, but you are able to input more than 12 bytes into it, for 13 bytes, 14, 15, 16. This can cause a modification in the nearby memory location, because we will see how it affects. Now, before actually practically looking at that, it works like you have an input function just gets. Now gets will start taking the input in the buffer, but since it does not know how many bytes it needs to copy before it stops taking input, it will copy all the bytes from the input unless it encounters a new line character. So if your buffer or if your character array is of, let's say, 12 bytes and you have input more than 12 bytes, say 20 bytes, so the remaining 8 bytes will also be copied in the buffer. Now since the buffer was only 12 bytes, the remaining 8 bytes will move to the nearby locations, thereby essentially corrupting the memory of that area. Now not all buffers can be overflown, and probably not all overflown buffers can be exploited, but those which can be, if controlled precisely, they can yield a shell on the system with UID root. Of course, this is conditional. For example, if your program is not running as root and it gets you a shell, then it's not UID root. But you get the point. The whole point is to say that you get a shell, and eventually you should be able to leverage some things and get privilege escalated to root, which is the ultimate goal if you're a pen tester or hacker or alike. Now let's look at how buffer actually corrupts memory, and then once we have a solid understanding of that, we will see how it can be leveraged to gain code execution. So let's head back to our Ubuntu machine. So first we will be looking at a basic.c file. So what it does is, let's add something into this, and volatile int x. Let's set x equal to 0, so that, and after we get it, let us print the value of x. Contains right. So we will be able to see if we are overwriting the character buffer with more than 28 bytes, what happens. So we are compiling it with several flags, which you can see. So the first flag is ethnostack protector. What it essentially does is, it introduces a stack cookie. So if you are trying to smash the stack and trying to override the return address pointer, it will do the cookie matching thing. It will match the saved value of cookie with somewhere in the memory, and if those values don't match, you have essentially overwritten past the buffer, and therefore the program's memory is corrupted and it needs to be aborted. Now the -z exec stack, what it does is, it tells the program that the stack must be executable, so that if we are putting our shell code on the stack, which we will be doing, it needs to be executed, else by default the stack is non-executable and we cannot execute whatever is on the stack. Now this is no rel row. Now this is a protection named by the name rel row, which is read only relocation protection kind of thing. So it is there to protect the GOT and PLT entries from overwriting. It was introduced some time back, but yeah, just for the kind of making sure that nothing hits us unexpectedly. Now this option, this flag is pretty interesting. So what it does is it sets the stack boundary to 2 raised to power 2, which is 2 raised to power whatever you tell it here. So 2 raised to power 2, 4 bytes. So now once that is done, let's just try to run this program and okay, enter something. That's 8 bytes. So and since we had a buffer of 28 bytes, nothing is overwritten and x contains none. So let us see what happens if we try to overwrite it with more than 28 bytes. Let's first start with 8 bytes or 28 bytes only. X contains null or x contains 0. What is said to be. Now what happens if we go ahead and try to send more input than the buffer is capable of holding? So you see it was only 28 bytes, and when we sent it 29 bytes, the next byte, which was a, and a in hex is 41, it overrode the value of x. So and since x is 4 bytes in size, the upper 3 bytes are still zeros. So this is how practically a memory corruption bug happens. You know, this is what we will be trying to exploit. Now what we did is to overwrite this value. The question now comes is how to gain the control of the execution, or how to control EIP, which is our actual goal. So let's first disassemble it. Object dump and let's just grab for main and print 20 lines. So yes, so this is our main function starting from here till here. What we can see is it is subtracting 32 bytes, 20 in hex, 16 into 2, 32 bytes in decimal, and we have push EBP, which is 36 bytes. So we should have a return pointer when the start underscore let's see main calls the main function. We should have the return address before this push EBP. Now what we see is 30 bytes, 32 bytes here, and probably 4 bytes here. So let's just write this input 32. Actually, let's make it 28 plus 4 bytes of B plus 4 bytes of C into input file, and load the program in this GDB, break on main, run with the input. Now what this does is you can run the program with input stored in a file. So what this does is it will read the input from the file input and connects it to the standard input, or send it to the standard input of the program, which the gets here will take and store it in the buffer. So let's just run the program. Sorry. Now we say this is we have stopped at the first instruction of main, and this is the return address which is on the top of the stack. Now if you don't have the Jeff thing with you, print one word in hex from the top of the stack, and which is this address. Now if you try to disassemble this thing, so we are at libc underscore start underscore main. So this is the function that calls main and does the pre-processing and things like that. So we are pretty sure. So what we have to do is we have to overwrite this location which contains this return address with whatever we have it. Now let's disassemble the main function and put a breakpoint at the return address over main plus 61, break main plus 61. Now if we continue, it has read the input, and let's see what we have at the top of the stack. And it says it has nulls, right? The last thing got overwritten by null. So what we can expect is our input wrote just before these 4 bytes, just before this address. So the last byte, after the input was read, the new line was replaced by the null, and hence we have the null. So let's just do that. Let's add 28 was here and 36. Now let's again run this with input, and what we see is since we ran it from the starting, this is our return address, and if we continue, we are at a second breakpoint, which is breakpoint 2 at this location, which is the return. Now the return address contains 4 B's. If you print the EIP, the top of the stack, X word in hex from ESP, it contains all 42s. So that means we are able to overwrite the return address. So because if you try to press SI, and it will say it could not found this address 42 42 42 42 in hex, and therefore this was loaded in EIP. So this confirms that we can overwrite the EIP, or we can control the EIP if we precisely put our input. Now the question comes how to move from here. So let's first get out of the debugger, and for now let's disable ASLR. For those who don't know what ASLR is, ASLR stands for Address Space Layout Randomization, and it is a protection mechanism which randomizes the base addresses of executables in memory. So things get kind of at offset basis, and they always randomize, so you never know what was the address of the buffer where your buffer starts. So you cannot be sure where your shell code starts from, since you are putting that in your buffer. So to disable that, echo 0 into procsys kernel randomize VS space to verify if that is there, randomize VS space, and it says 0. Okay, so we have exited it, and to verify that things are loading at the same location every time, you can try to run this program with LDD. Now you can see that this library was loaded at this address B7FD9000, and see, so yes, our ASLR is off, and now we have made sure that our addresses will be static. We can use them as return addresses. So we have done that. Now if you remember what our program was, it was this, and we effectively control the EIP. Now before trying to inject external code, what we can do here is we have another function which is not called in our program, which is the win function. So let's try and call this function so that we can just kind of see that we are good at controlling the EIP. So to obtain this token address, let's just grab it from the object dump. Here we get, this is the address, and Python, that's it. Since we are doing on an Intel 32-bit machine, this is a little endian machine, and therefore we have to write this address in the reverse order. So that is 08, and you see we got the output code flow changed, which is this. So this is precisely what we are going to do in the remaining part of this video, and probably in everything if we are concerning with the expert development. So make sure you are able to reproduce this, and now let's head back to our shell codes. First, what we should do is, okay, we will first try it with our exit one shell code. So if we run this binary and give something like hello, our exit code is 1, if we can, our exit code is 0, which we can verify here. If you remember in the past, in the previous video, what we did was we wrote a shell code which exited with 1. So we will try to execute that shell code and try to return as 1, just to gain an understanding of how to run our shell codes. But before that, now we have a problem. We don't know the location of the buffer. Well, not yet. We'll see in the debugger, but yes. So the strategy is to send the bogus data, since the first 36 bytes are just to reach the return pointer override. So we can have anything in our first 36 bytes, and then the 4 bytes are used to control the EIP. So what we are going to do is to override the EIP, or the saved return address, with the location of our buffer, and since that is the location where our input gets into, and we will put our shell code in that location. So let's get started. First, we will see the location of our buffer. So what we have here is this. Now gets take an argument which is the location from where it has to store data. So push EAX, and so this is the argument, or this is the address where the gets will put the input into. So let's just break into main plus 29 and just print the value of the EAX. Continue IR EAX. So this is the value, or this is the location of our buffer. So let us say print 15 words in hex from this location. So what this contains right now is this bogus things, which is the chunk data. And now if we run this, we will get exit because there's no stopping. So what we will do is we will put a breakpoint just after the gets, so we can verify that this is the location. So break main plus 35, the very next instruction of the call gets. Break plus 35, continue, and here we are. So if you remember, this was a location, and see, we have overwritten with 36 A's, oh, well, whatever that is, and then we have the our return pointer override. This is it. Okay, so this will be our location. Now let's just see what we had in. We had around 36 bytes. So those are not 36 bytes bring in, yeah, you get the point. So we have 36 bytes and then the return address to override. So what we can do is we can generate a shell code and put that, but for now what we are doing is we are just taking this shell code, which is let's see how many bytes, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 bytes in size. Let's verify Python. Okay, yeah, it's 10 bytes in size. So 36 and 10, we have 10 bytes for the shell code, we are left with 26 bytes. So what we can do is with 26 bytes, we can put no in their place, so that if our EIP gets to that location, it doesn't matter, it will just execute nothing. And now I forgot what was the location of the buffer. So this is the location of the buffer. I just copy it into another window so that we know what the value is. Yeah, I'm pretty lazy with this thing. Now, so Python minus C. Let's just remove this thing. And 90 is the output for NOP. We had 26 for that. Plus, we will be this is it, or 10 bytes. Copy and paste it here. Then this is the place we have to overwrite our buffer with, and the address is p8ef p8e8 ffpf, and you see we have a segmentation fault. Now we got a segmentation fault because when you load the buffer inside, or when you load the program inside a debugger, GDB in this case, something offsets change because the environment changes in which the program is running. Therefore, we need to see what the value is. Now, let's kind of verify that the environment is changing. No, yeah. First, let us verify if we got it correct or if we overwrote that properly. Send it into the file GDB break main, run with input, disassemble main. This is it. So what we're doing is this. Let's break here, break main plus 29, and the next should be break plus 35 to verify that input was taken at the right place and inspect that what we sent was correct. Then let's just break at the last main plus 61, which is the return, so that we can see what our return was written with. Now continue IREX, which is this B8. This is B8, and what we had here is it was B8, so we are correct in this at least. Now let's just clear the screen and 15 words in hex from this location, and this is the bogus data because we have not yet taken the input from the file or from the standard input. Let's continue, and let's just again see we have this thing, our nulls, sorry, our NOPs. We have 26 NOPs. Then we have this thing, and this is our return address. So let's continue and see what the return address points to. This is the return thing, B8 F. Oh, sorry, I think we overwrote the return wrong value. F8. Let us see. E8 B8. Oh, sorry, that was F8. Okay, EF B8. Okay, EF. So that should do. And basic from input. Yeah. So it still crashes. Let's see what happens or what actually happened. So B8 EF, B8 EF, FF BF. Okay. So we have written the properly. Right. Main run with input. This is a main plus 29, main plus 35, and main plus 61. So we got 4 breakpoints. Now let's continue. IREAX. We have this location. Examine 15 words in hex from this location. We got this. C. And this is our input. So we can see that we overwrote this with this is the return pointer, which if you remember, and we overwrote it with the location this. So what should be that this should get here and execute. Now let's continue and see this. So the return address, the EIP is, well, yeah, we haven't returned, so the EIP is the last. Now if IREIP, see, we are at this location. Let's just have it here, and this was our buffer. So you see the EIP is the same, but now you can say that if the EIP is same here and we are coming at the right location, what was happening? Now this is why you need to adjust some offsets outside the debugger. So let's just continue this, and so inside the debugger we see that the interior process 1 exited with code 0. The problem with this is okay, so coming back to this thing, we saw in the GDB that offset was not what we saw when we tried to run the program. So let's try to run the program in the ltrace. Now ltrace is a program that traces the library calls as they happen inside the program. So let's just try to do basic with the input, and it says the first argument is the location. So this is it, 028. Let's just try to write this. I've written this here, you can see, and input, and let us say basic and input, and if we do echo $, we see the exit status 1, whereas so you can see that the exit shell code got executed. Okay, so in this part we saw how we can execute our arbitrary shell code which we injected. Now for the exercise, what you can do is you can try to execute some other shell codes which you feel like doing, like reverse TCP, bind shell, or whatever. Just make sure it is executable, and yeah, the offsets will change inside the debug and inside the debugger, outside the debugger. So make sure to account for that. Now in the next part, we will be looking at how to well, actually we have 2 things to discuss in the next part. The first one is how to bypass the restriction of executable shellcode, or actually the non-executable shellcode, which is the stack is non-executable. So what will you do in that case? And another thing that we will look at is what happens if we don't have any space. For example, here we saw that we had only 28 bytes, or actually 36 bytes of space, 34 bytes of space, but our shellcode, even exit shellcode is something you can do anything with, right? But or even the hello world shellcode was something like around 35 bytes in size. So yeah, that's something you should know. So we will see how to deal with that. For example, 30 something bytes are sometimes probably enough for an egg hunter or things like that. But for example, what you have, what will you do if you have 8 bytes? When our exit shellcode was of 10 bytes, yeah, you can write a smaller one if you feel like so. But what I'm saying is you can do anything with the exit shellcode. So to do something productive, we will see what to do when we have a non-executable stack or we have a very limited space. So the next session, the next video will be the final video of this session, which I delivered. Then after those videos, we will be looking at the ROP, return-oriented programming, how to defeat data execution prevention, DEP, or non-executable stack with ROP. And we will be looking at some examples, some procedures. We can optionally see some other things in action, such as some vulnerable VMs and challenges, things like that. So make sure you subscribe to the channel, and if you like the video, leave a thumbs up. Any comments would be appreciated, feedbacks would be appreciated.